Of Mike Ireland talking about the orbital motion and multi-wavelength monitoring of LIGCA 15B.
Great, thank you. Thanks very much for having this opportunity to tell you about just one object instead of a whole class, but a very, very interesting object, LIGCA 15. Here we have sort of an artist's impression from a paper that Adam Krauss and I put out last year of a planet in a transition disk, of which there's a whole range of different artist impressions these days. And yeah, this work's mostly done with Adam and myself. So I'm going to motivate why we bother looking at objects like LIGCA 15 very briefly. I'll tell you about some very interesting technical details and then get into the science or the astronomy. You can spend a lot of time looking at distributions of old planets. GPI will discover a whole bunch of them, I'm sure, and it'll be exciting. But looking for newly formed planets or planets in the process of formation is a different game altogether. And there's two fundamental reasons why. One is that when you see planets in the process of forming, you know where planets formed. If you see them 100 million years later, all sorts of things, both migration in the disk and planet-planet interactions can happen. Secondly, young planets are much brighter. If in the hot star models, they're significantly brighter. In the cold star models, they're even brighter again if you happen to have core accretion occurring right at that time. So this is a Miley model down there. But there's a problem. The problem is that to see young planets in the process of forming, you have to go out to objects, places like Taurus, Upper Scorpius, Rho Ophiuchus, all at about 150 parsecs, where 5 AU is 50 milliarc seconds, 1 lambda on D, right at the diffraction limit of a large telescope. So part one of the solution we've seen a lot of, especially yesterday, adaptive optics. It's a magical system where the aberrated wavefronts from the atmosphere get correctly, perfectly corrected, and then you can analyze the data exactly like Hubble Space Telescope. It doesn't quite work because there's always small instabilities, and here's a couple of pictures I took at Keck and I think that's the wrong button, isn't it? There we go. Where you can see a small difference in the first area ring here, with apparently no change to a very stable AO system. So you have to fix this problem somehow if you want to be able to detect planets that are more or less right in the core of this area disk. So here's the technical bit. People talk about algorithms like Loki, which are wonderful thing invented by David Lafreniere, and there's the even better, in my opinion, algorithm CLIP, and a poster by LED out in the poster room. But all these kind of techniques to remove speckles are essentially removing something that's first order in pupil plane phase errors. So what do I mean by that? You've got some perfect diffraction pattern, and then you add a bit of a corrugated wavefront, and the speckle error you get is linearly proportional to the corrugation on the wavefront. So you're removing something which is very easy to change. First order in phase errors. You can make things a little bit better by using a coronagraph. And if a coronagraph is perfect and removes a flat wavefront perfectly, puts it all outside the Leo stop, then what you're left with is just speckles that are second order in pupil plane phase errors. And that's good. It's better. But we can do better than that in terms of calibration. We're talking about calibration here, not photon noise. And we can use this technique called kernel phase. And that's what aperture masking interferometry is all about, including aperture masking without an aperture mask, which is what Franz Martinach in particular has termed kernel phase. So I'll just stop for a bit and explain what this is and why it's important. So the slight difference in this technique compared to others is that we're working in the Fourier plane. So we take the pupil of a large telescope, and we have a typical one that looks like a donut because of a secondary obstruction. You take the Fourier transform of that by taking an image in a detector, then you take the Fourier transform of the image, and you get the autocorrelation of the pupil. And you'll see that when you take the autocorrelation of the pupil, this dashed line is bigger than that line there. So you basically have, if you have so many sort of pupil plane pixels, you have 4 times as many Fourier plane pixels, and there's this factor of 2 redundancy because one half's the conjugate of the other, but you have twice as much information here as you do opportunities to make an aberrated wavefront up the top. So no matter what you do with the telescope pupil, at least half the information in the phase of the Fourier transform is totally independent of corrugations to the wavefront. So you can remove all these effects of defocus, coma, whatever, little misalignments at first order in phase, and you're just left with third order errors. And so that's what this aperture masking, well, that's what kernel phase is all about. So often that's not quite good enough, and we also use this thing called an aperture mask to modify our pupil. In terms of the analysis, that's sort of a detail, whether you've got a circle or lots of little holes. Adam Krause is going to be talking on Friday a bit more about aperture masking in some of our bigger surveys. But yeah, the basic principle is it doesn't really matter whether you have a single image or a big image like this. You still basically, in the Fourier plane, sample all the information in U and V. So a full pupil has lots of baselines. Each baseline comes from a very large fraction of the pupil. A non-redundant aperture mask, each baseline just comes from a unique pair of holes. But in the Fourier domain, you still have basically the same information. The trick is you have to, of course, use radio-based imaging techniques or direct forward modeling and fitting in order to determine what's going on for your astrophysical source. So I'm talking about this as a little bit of a tangent, partly because I've got a result from full pupil kernel phase, but I also think it's going to be sort of a much more important technique in the future. And the reason is that at low strels, you've got some sort of phase error as a function of spatial frequency here. So you have some sort of pupil plane phase, you basically get the same error in Fourier phase, and you get a bit screwed. With an aperture mask, you can clean up the wavefront very well at low strels. Particularly the work with Mike Lude, Trent Dupuy, with laser guide star AO shows that works very well. But when you get to very high instantaneous strels, you don't really need the aperture mask anymore, and you can just use this kernel phase technique just with raw images. And I think that's going to be the future of a lot of high contrast imaging right at 1 lambda on D with things like GPI. So let's get back to astronomy. That's a technical detail. That sort of explains it very quickly where some of these images are about to come from. So using mostly aperture masking and this kernel phase or closure phase techniques, we spent a lot of time looking around these transition disk objects. Here's the torus ones, or the torus region on the sky. But we sort of looked at about a dozen transition disks, spent quite a long time per target in the end, like nearly 4 hours, getting down to nominally, with hot start models, few Jupiter massage limits, and basically didn't really detect anything, with one clear exception, and that was an object in the hole of this disk, calcium-15. So there are other potential detections, but nothing clear. So what's calcium-15? Why do we care? It's been in a slide of most of the talks in the last 2 days at least once. It's a transition disk or a pre-transition disk, depending on how you define these things. A big inner hole that's resolved in submillimeter. So it's a hole at least in the dust distribution, large grains. And there's this lovely Subaru scattered light image of what was taken by what was modeled to be sort of an inner disk wall here imaged. A hole of about 46 AU with caveats on submillimeter analysis, a 50 Jupiter mass disk. And the star has a very well-known mass, 1 solar mass. And it's part of Taurus, so it's got a well-known age, 2 to 3 megayears. And here was the result from 1 year ago. The summary slide, there's a very long paper on all the details of, unfortunately, something that's not very simple. Something where there's blue here meaning K-band, 2.2 micron emission, and red meaning L-band, 3.7 micron emission, extended 10 to the minus 3-ish L sun, interpreted as sort of being a planet plus co-orbital material, a separation of sort of 20 AU once you take the inclination of the disk out. So 46 AU hole, 20-ish AU planet, or object, let's call it. So we've taken a lot more data, and that's kind of what this talk's supposed to be about. So originally we just had a survey of Taurus, and then we started detecting very interesting things here in 2009. Unfortunately, it turns out, well, in the coming slides, things have been a little bit variable. It would have been nice to have everything simultaneous, but the weather hasn't really allowed that. So So we have observations in H-band, K-band, L-band, and M-band. So H-band, we've spent a lot of effort on. When I put everything together for H-band, I don't detect anything. So aperture masking, the analysis technique that we use at the moment, it's got some sort of outer limit, which is 200 milliarc seconds in H-band. We can't detect anything beyond there without changing the software. The star in all these images is subtracted. It's only the point antisymmetric component that we're really imaging to. And the brightest noise peak is about 1,000 to 1, but there's essentially nothing there. In M-band, well, this is M short at Keck, so 4.7 microns, we detect basically exactly the same thing as we detected in L-band. It's quite a nice image, but part of the reason it's nice is because of this beautiful kernel phase algorithm. Part of the reason is that this contrast is very moderate, only 3.5 magnitudes once you integrate all the light here. And when I say 3.5 magnitudes, usually I never use one of these maximum entropy reconstructed images. I sort of split this into 3 point sources, do a forward model, and then get the flux from that. K-band, 2 epochs. So again, there's the different imaging algorithms that give different results here. And also, so 2010, this first epoch in this animated GIF has one clearly bright source in the middle. 2012, it doesn't look like that at all. It's these sort of lobe sources have got quite a lot brighter. It's on roughly the same scale. And if you squint and look very closely, this moves by a couple of pixels, that moves by a couple of pixels, this moves by half a pixel. If you sort of change the imaging algorithm to make things peakier, you can always tweak things with things like maximum entropy. You see the same consistent motion of something like 3 to 4 degrees per year. But let's keep going. Is this real? I've got 2 other analysis techniques. So here's the 3.7 micron images. Again, things appear variable, which is interesting. And if you squint again, you can sort of see it starts at 2009 and goes through to 2012. Things do sort of appear to be going in a clockwise direction. That's okay. So orbital motion. If we, instead of doing these fancy maximum entropy images, fit 3 point sources, try and fit lines to it, it's quite clear that, that there is this clockwise orbital motion of about 3 to 4 degrees deprojected, or 6 degrees in the raw images per year. And it's sort of 1 to 10 sigma, depending on which blob we're watching move and which filter. So why is this important? Why does it matter? Well, it means the geometry of the Thalman paper from Subaru is correct. You've got red shifted, blue shifted, background, foreground, side, and this sort of north westerly side really is the illuminated wall side of the disk. It also means that you can't put any exotic forward scattering as an explanation of this material. So seeing I'm sort of out of time, I'll skip this other than saying here's the original sort of figure from the paper a year ago where we sort of talk about the potential central source as sort of matching-ish a hot start model at 6 Jupiters. But remember that the entire emission here is much redder than any planet model and also a bit brighter. So hot start models are really not the way to deal with this data. So I spent a lot of time trying to fit scattering, originally before I'd figured out the orientation of the disk, thinking of exotic forward scattering models. But basically, the emission is very red. So here's the sort of numbers. Because of variability, there's a range here. Red colors all the way from H to M band. And basically, with any actual real physical dust, that I could never come up with any way to get an extremely red scattering. So if there's not scattering, it has to be thermal emission. Basically, 1 slide to go after this, so I think that's right. And thermal emission is crazy. An extended thermal emission, so this is like 10 AU across at this radius of 20 AU. To actually detect anything in K-band from thermal emission means you need many hundreds of Kelvin. So the equilibrium temperature here, this place in the disk, is something like 200 Kelvin, 250. You can push it with small grains, but that's this red curve here, absolutely nothing to do with the flux that's measured. So you need to magically somehow heat this dust up to 900 Kelvin to make it glow in order to match all these different infrared objects. You have to do it in a variable way because things change as a function of time. Which is absolutely crazy, but very interesting. And it's going to have something, in my opinion, to do with accretion in luminosity. And apparently, this is not a point source with a single dot of emission where the accretion shock hits the photosphere. We have something that's much more complicated. And something like a few by 10 to the minus 3L sun is exactly what you expect for a few Jupiter mass object as it's forming. And remember, we looked at a whole bunch of transition disks to the places where planets are supposed to be forming. And we detect nothing except for this. If there's going to be accretion luminosity anywhere at this level, it's going to be around this one object. And that's exciting. So lessons learned and what comes next. This object it remains complicated. But we would have had no clue at all what to publish if we didn't have a lot of extra data on this object. So in particular, the millimeter CO dust measurements, the continuum measurements, IR spectra to eliminate crazy things like PAR, multiple wavelengths, orbital monitoring. We need all this stuff to make any conclusions. But there's still a lot to do because it's a crazy system. It's extended hot dust where we don't know really the physics of what's heating it up as interesting. Something like looking for accretion shocks with H-alpha, like what Laid Close plans to do. CA's poster is definitely a thing to do. Polarimetry can tell you about scattering. Unfortunately, we don't have a good instrument for that in the northern hemisphere. And the one in the southern hemisphere is being decommissioned, but it's something we can certainly do in time. And of course, as soon as ALMA gets 2-kilometer baselines, hopefully we'll be able to see extra things there too. I remember point source planets are boring, and the action happens at young ages. Thanks.
Thank you, Michael. I think we've got time for a couple of quick questions. James?
Well, I will holler.
Yeah, it's coming.
So I had a question and a comment. Thanks for a great talk. The question is about temporal coherence timescales and what temporal coherence you need the AO system to deliver for this to work.
So these are long exposure images. So
compared to the tau naught.
Compared to
tau naught, or
compared to
what's the physical timescale relative to which it's long?
The physical timescale. You're talking about the technique or the physics of the things changing?
Oh, forget about the astronomy.
Okay, you're talking.
Let's talk about science.
So the length of time. So the initial images, we're talking about 20 minutes of data in total. For the deep H-band non-detection, that was 6 hours in total. The AO systems are running at 150 hertz often. For some of these, it was a bit faster for this. But this is a 12th-ish hour of 12.
But the individual frame time is what?
Oh, Keck doesn't do short frames. So it's 10, 20 seconds. Yeah.
Okay, that was the...
Anything longer than 100 milliseconds is long in this regime.
Yeah.
We've got a recent paper on this.
And the comment is that the GPI input catalog is extraordinarily sensitive to the heat of formation of the planets that we will see it. So it's not that we will not tell you what the Kelvin-Helmholtz time is. You know, the Kelvin-Helmholtz time is hundreds of millions of years, and so we'll be able to discriminate between hot start and cold start. We won't see that spike, that accretion spike. So they're different questions.
For the near-infrared photometry, could you explain again why it is that it can't be reflection? Is it just too bright?
Explain why it can't be...
Reflection.
The colors. So in M band, it's a little bit too bright. So at 4.7 microns, 3.5 magnitudes contrast, that doesn't quite work out. But the real reason that I can't get it to work is that the colors are extremely red. So if you sort of integrate the entire shape, so it's 3.5 magnitudes contrast in M band, and in H band at 1.5 microns, it's at least 7 magnitudes contrast. So you have extremely red scattering. So to do that, I could do that with grains that basically the imaginary component of the refractive index went up by a factor of 10 between each band. And there's no physical grain that I know that does that. I'm not sure who I'm talking to, by the way. Yeah.
Okay, let's thank Michael again.